This series of videos marks a change in what we're studying in calculus. That's not to say we're not going to look at derivatives anymore. They'll show up here and there, but we're going to turn our attention to a different branch of calculus. Before we do that, let's remember how we started when we looked at derivatives. Recall that we started looking at derivatives with tangent and velocity problems. Given a function f and a point on the function, we can, if the function is differentiable, find the equation of a tangent line to the function at that point. And remember, the slope of the tangent line, generally change in y, change in x. But then we saw that through the limit process, that becomes dy dx. If the units of the x-axis, the input, are time, let's say seconds, and the output, or the units for the y-axis, are in distance, say meters, then the units for the slope are going to be in meters per second, and that's velocity. So depending on context, the derivative of a function can represent the velocity of some particle moving in a way that's described by the function. But more generally, the derivative is a function that gives us the equation or the slope of a tangent line. Something similar is going to happen now, except it's vastly different. Suppose I have a function that represents velocity now, right? So this is a different situation. And let's say the input is time, again in seconds, and the output is velocity, say in meters per second. Then we could find a derivative, and that would give us a tangent line, and the slope of the tangent line would be in meters per second squared, so acceleration. But I want to do something completely different now, so I'm actually going to get rid of all of that. And let's say I'm interested in, instead of a slope, the area under the curve f from A to B. We'll see how to deal with the fact that the top edge of this region is kind of irregularly shaped. But if we think about units of area, I wasn't going to do this yet, but I don't think there's a way around it. Let's chop up this area into a bunch of vertical regions. These aren't exactly evenly spaced apart, but that doesn't matter for what I'm talking about. Let's pick one vertical region in particular, and let's say I want to approximate the area of this rectangle. So I'm going to use, I'll just finish off the rectangle. And you see what I've done is I've used the function height over here as the height of the rectangle. Suppose I label these vertical lines here like x1, x2, x3, x4, x5, x6, x7, and then b, I'll say it's x sub 8, and then a we'll say is like x sub 0. Then the height of this particular rectangle is going to be f of x sub 4. Don't worry about it being 4. And then the width of the rectangle we'll say is, you're used to this, we'll say that this is, it has a width of delta x, just some increment on the x-axis. Then the area of this rectangle is height, f of x sub 4 in this case, but you're really not going to care about 4, times delta x. And if I repeat that process over and over, then what I'm going to have is the areas of a bunch of rectangles that are going to come close to the area under this curve. Now don't worry so much about that process right now. What I want to focus on is the units. The units for the function are meters per second. And the units for the input, or on the x-axis, are seconds. And so the units here are going to give me meters. Here's the point here. If my function is a velocity function, finding an area from one x value to another x value is actually going to be akin to finding a distance. So instead of mixing units using division, like we would for a tangent line, we're going to mix units now using multiplication. Generally, this is an area, and in a particular context, that area can represent a distance, like a distance traveled by an object whose speed now, or whose velocity, is described by the function f.